Hi, my name is Arya Karnik, and I'm a computer engineering major here at the University of Alabama, working on building a small uncrewed aircraft system with 6 degrees of freedom to emulate satellite dynamics. I'm working with Dr. Jordan Larson and Philip Varnado in the Department of Aerospace Engineering and Mechanics through the Lager Laboratory. First, I'll start off by giving a quick presentation outline on what we'll be talking about today. First, I'll give a general project introduction so everyone can understand what we're working on. From there, we'll move into the objectives of the project, what we're trying to achieve, and talk about the design overview, understand what we're actually building and how we're going to achieve our goals. We then will talk about system components and capabilities and understand how the different system components actually help us achieve our goals. And we'll look at the developmental flowchart to understand where we are in the process and what the next steps are. From there, we'll talk about future work and the applications of our technology into the industry. First, a quick overview of what is a small uncrewed aircraft system. Essentially, it just boils down to being an FAA classification, which is the Federal Aviation Administration. The main thing is that you need to register the drone you build and needs a Part 107 pilot to fly it. And it must be less than 55 pounds. This is a very important fact because it means that it's a small testing package, which is very crucial for what we're trying to do. For example, if we crash the drone or something happens with the drone, since it's a small drone, it's affordable for us to fix and we can do many different prototyping quickly, fastly, and most importantly, at a price that actually makes sense for what we're trying to achieve. As you can see in the image there, that's a typical size of one of these small uncrewed aircraft systems. They can range from 1 meter to 3 meters in length and width, but in our case, it's 1,000 millimeters length and width across. Our project objectives are, as stated earlier, we're going to develop a drone system to tackle satellite CONOPS. CONOPS are satellite concept operations, and these include rendezvous missions, docking missions, and things along that nature. We also will be developing an indoor and outdoor testing platform, which then we can understand how our drone works with different constraints and capabilities, both with weather, with sensors, along those lines. We also want to implement a base flight control model, and this is important because when we actually work with the 6 degrees of freedom drone, which I'll talk about in a future slide, we can understand how that flight control model works and then iterate based off that design. We also will emulate rendezvous and docking missions, as I mentioned previously. This is important as this will allow us to actually emulate satellite dynamics on Earth, both indoor and outdoor. We also want to advance autonomous control systems. So when we build our second drone, we'll actually be able to understand how drones work together, both in an autonomous sense and also in a manually controlled sense. Currently, there's a lot of issues with how the current industry is trying to solve these issues, but by building this drone package at a small, affordable cost, we'll be able to hopefully produce novel ideas and solutions to actually advance these control systems. So what is 6 degrees of freedom? I mentioned that multiple times in this presentation so far. Essentially, what it boils down to is that the drone can translate and also rotate across the whole axis in any field of motion. This is very important because a satellite has 6 degrees of freedom. So for example, it can hover in space, turn left and right, yaw left and right, also pitch up and down. This is incredibly important, and our drone design will be able to hopefully emulate this objective. And that, in turn, will help us with our autonomous control systems, alongside also with our rendezvous and docking missions. From there, moving into our design overview. We're working with the PX4 Omnicopter. And an Omnicopter, as you can see the image here, is a very valuable piece of this testing platform. It is essentially a box with each motor, the 8 motors that are on there, providing both thrust and control to the drone. And I'll get into that in a future slide, but essentially what that boils down for now is that it will allow us to have precise movements when we're actually developing our autonomous control packages. In terms of our hardware choices and software choices, we're working with the Sparrow flight control system. And Sparrow is the Simulink/C++ platform for aeronautics and autonomy research and operations. This is important because this platform allows us to essentially be able to code our flight controllers using C++ and Simulink and then instantly add that to the drone itself. We also are using Onyx 3D print material plus carbon fiber. And when you look at a drone at this size, 55 pounds or less, an incredibly important thing to consider is weight, right? Because we only have so much batteries we can put on there. We need the drone to be able to fly. By using carbon fiber and Onyx 3D print material, we're keeping weight light, but also very rigid and structurally integral. This is important because Onyx is nylon and carbon fiber that's basically filleted throughout the print material. And this allows us for the drone to be light, but still be very strong and durable. We are also using the D-Shot protocol instead of PWM. And PWM stands for pulse width modulation. These are both technically digital signals, but D-Shot is, in essence, a true digital signal. And for the purposes of this presentation, it essentially boils down to the fact that PWM suffers from things like jitter and also needs calibration, while D-Shot is straight ones and zeros. This means that we can use precise control movements and precisely say, okay, we want it to be on or we don't want it to be on. Well, with PWM, we sometimes have jitter where, it might be on, might not be on. And this is very important for when we're working with autonomous control systems, rendezvous, docking missions, with a secondary drone as well. We want to be sure that we can precisely control the movements of this drone and understand what's actually happening. We also will be using electronic speed controllers to control the motors. And from there, we can now take what we've used on the design overview and talk about the system components and capabilities. As I mentioned earlier, we have 8 motors, and these will need bidirectional D-shot, which is something that we're currently working on right now to tackle. It needs bidirectional D-shot because, as I mentioned earlier, each motor provides both thrust and control, right? However, for that to be the case, the motor needs to be able to spin both clockwise and counterclockwise, and that requires a custom driver that we're currently working on. However, unlike traditional drones, omnicopters are equipped with these rotors that are positioned at these certain angles that you can see from the paper from Brichoni that basically allow us, as I mentioned earlier, to have both thrust and control in our drone. This is achieved because the way the motors are positioned at different angles allow it for that to be the case, and this is great for us because it allows us to have both that 6 degrees of freedom motion and be able to yaw one part, spin, turn, whatever we need it to do. We also will be using the BFS, Boulder Flight Systems, FMUR, which is the Flight Management Unit for Research. And this will allow us to gain access to unparalleled levels of telemetry data that we can then use to iterate on our designs. So now, the grand reveal of what actually is our developmental flowchart looking like. First, obviously, to start off with the drone, we need to actually build the airframe. So building the airframe. From there, we can take the built airframe and actually start testing the hardware. And this includes testing, making sure that all the joints fit together, the carbon fiber that we cut and hand milled, understand that actually all works together. We can then move into hardware integration, actually integrating the different parts, integrating the motors, the propellers, and then finally integrate the flight controller. And with integrating the flight controller comes actually flight testing with the flight controller. And this is kind of where the start begins of understanding our base flight control model, how that works, and iterating based off that for future designs. We can then integrate the unit that provides the research, the FMUR, to then start getting access to our telemetry data. And from there, we can then move to work on Sparrow software code development with our long-distance master's student and understand how we can then take the proposed model from the original paper and iterate it to work better with our designs. We also will then be doing flight testing with FMUR, gaining access to that telemetry data as I mentioned earlier. And from there, we will then build the secondary drone. And this will be a great step because from the secondary drone, we can then get access to the rendezvous missions, the docking missions, understanding how we can then develop our autonomous code package. And that will be the next and final step. And after we can fully start developing that, and everything I've mentioned, by the way, should add as a clarifier, will all be iterative processing, right? So we might do one of these things, have to go back and understand, hey, how can we improve this? What's going on? The situation might present itself that we actually need to go back and change one line of code. And then finally, we hope to then develop innovations in satellite CONOPS, which leads us into future work. What do we actually want to do with what we're achieving? First, we want to fabricate a secondary drone to develop its satellite CONOPS, concept operation plans. From there, we want to work to implement the improved flight control model based on the original paper. We will then test and contribute our D-shot driver that I mentioned for the bidirectional motors for BFS and Sparrow, so we can then also help everyone else move off of PWM and start working on D-shot protocol. We also will then hope to propose innovations in autonomous control systems. Thank you so much for everyone's time, and now I'm open to any questions.
On slide 8 in your flowchart, the Sparrow software development seems to appear like mid to late phase. Why is that? Why can't you, through some specs or something, begin the software development earlier?
Yeah, that's a great question. I think ultimately, like I mentioned earlier, the first main part that we're kind of stuck at right now is developing that driver, right? So essentially, before we can even start developing the software, we need to understand, hey, how can we actually code these motors to do what we want? So that's what I've been working with Philip and some of the team on, is understanding how we can actually code this D-shot driver. So in essence, yes, like you said, like it is a parallel process, but the majority of the flight control model will come once we can figure out how we can get the D-shot protocol to these motors.
So when you're talking about simulating these CONOPS, like there are a lot of similarities here between the drone you're talking about and space vehicles, but there are also a lot of difference in terms of, drag, the gravitational pull, the type of thrust used. Do you anticipate there being any major obstacles in replicating those kinds of maneuvers?
For sure, and that's a great question. I think, obviously, like you just said, right, building a small 55-pound drone is nothing like the satellites that we go see in space. I think that's something that we definitely need to explore, right, and keep in the back of the mind. I think the goal and the idea here is that since it's 6 degrees of freedom, allowing it basically to hover and also have those translational moments and motions that we hopefully can accurately represent what vehicle dynamics look like in space. But that's definitely something we need to explore as we keep working on building these drone packages.
So how would you say the 6 degrees of freedom contribute to the overall performance and validation of satellite dynamics and when performing and designing satellite CONOPS?
Great question. I think, as I just mentioned earlier in the last question, something very important, right, is that satellites are 6 degrees of freedom, have 6 degrees of freedom motion. And allowing that allows us basically to essentially emulate, for example, docking, right? When the satellite's docking somewhere in space, it might not necessarily actually just need to move left or right, but actually you might need to stay in position and hover, get the correct pinpoint, get the correct connection point. So having that 6 degrees of freedom essentially allows us to then emulate that on Earth with these drones.
Add that second drone to the test package. How do you think that would help bring about some further improvements?
Yeah, for sure. So as I mentioned earlier, some of these missions in these CONOPS require 2 satellites, right? Like rendezvous missions, for example. Adding that second drone will not only allow us to understand, right, hey, how does this drone work with another drone, just on a drone-by-drone basis, but more importantly, also understand how our autonomous systems work, right? How do the sensors interact with each other? You know, is it actually detecting the correct distances, the translational motion between these 2 drones? And that all these things can help us iterate through the FMUR to understand the different telemetry we're getting in to hopefully improve the testing package.